Hello everyone, welcome to the very last unit of the course and obviously the last lesson of the unit. What we're going to do is look at inverse functions in this final lesson. It's a pretty important type of function and people tend to try to treat it for a lot more than it really is. Inverse functions are just a special graph relating to original graph. And you can see in some of my original notes we've got some fancy notation. But the key that an inverse is for every graph that there's kind of a graph that'll always undo it, or kind of an opposite, I guess is what you could think of it as being. And we have a special notation that we use for inverse, which you'll see shortly when I get to our examples. And there are some special properties that I want you to really read about in the first page of the notes. Inverses are not reciprocal. In Pure Math 30, you'll learn the difference between an inverse and a reciprocal, so it's key to understand that. And inverses can be done three ways, and I've got examples to show you how you can do each type of inverse. We're going to switch coordinates around. We're going to switch x and y and solve for y. And then we could look at a reflection on the line y equals x. That's something you do more in Pure Math 30, but at least I'll show it to you in this lesson as well. Inverses are basically a switching of domain and range. Whatever the domain and range of the original is, the inverse will be the reverse of it. Inverses will be reflecting over a fancy line y equals x. An inverse may not be a function, and you'll see that when you start to deal with some of these. Once you do an inverse, you have to check to see if the inverse is a function, and we'll see on example 2. We'll look at that. So if you ever want to determine inverse from a series of coordinates, our first example says find the inverse of these ordered pairs. Well, the notation we use for inverse is f to the negative 1. And what we want to do is we want to switch x and y. So if the point was 0, 2, the inverse point would be the reverse. Domain and range, switch. If the original point was 1, 3, the inverse would be 3, 1. If the original point was 2, 4, the inverse would be 4, 2. And if the original point was 3, 5, the inverse would be the point 5, 3. So it's really quick to determine inverse from a series of points. And you'll see in the first two examples that's what I tend to do, is to find inverse by taking points, switching x and y. And when I switch x and y, what I'm really doing is switching domain and range. The domain of the original was 0, 1, 2, 3. Well, the range of the inverse is 0, 1, 2, 3. The range of the original is 2, 3, 4, 5. The domain of the inverse is 2, 3, 4, 5. And we use that fancy notation f to the exponent negative 1 to indicate that this is an inverse function. So if you have points, switch x and y, and that will be your inverse. What does that look like in a graph? Well, let's look at two different functions here. What I'm going to do is, if you ever have a graph, find some important points off your graph, and I'm going to take these x and y intercepts and label these, and I'll draw my new inverse based on switching these coordinates. This is the point 2, 4, 6, 0. This is the point 0, negative 6. And this is the point negative 6 and 0. What we're going to do, and I'm going to change the color of my pen for this so you can see this a little easier, is we're going to switch x and y and redraw this graph. So the point 6, 0 becomes the point 0, 6. Alright. The point 0, negative 6 becomes the point negative 6, 0. And I need to draw the straight line from those 2 points. So I'm going to try and draw a straight line through those 2 points. So that covers that first leg to the vertex of that V. My third point is going to be negative 6, 0, which is going to be 0, negative 6. And now I'm going to draw the last part of that V. Nice straight line. Obviously I don't have a ruler. And that's what the inverse looks like. Now here's the neat thing. As we get a different color again. This is a reflection over a fancy little line. And it's a reflection on this line here that I have drawing in black here for you. And what I mean by reflection is it's a mirror image on this line y equals x. And it takes a little bit of time to picture this, but you can see that the original graph is almost like it's been folded over this graph. You can see the red and the black corresponding on the one side. On the other side, you can see as one's going above, the other's going below in the same direction. Inverse is always a reflection on that line. We talked about reflection on it back in quadratics over the x-axis. This is a reflection on another special line. And these two functions are considered to be inverse. Now, my next question then becomes, when you look at that red graph, is that red graph a function? And you should be answering not a function in this case, because it wouldn't pass the vertical line test. Notice this V now opens to the right, and you would have it crossing in 1 point or 2 points with a vertical line. So the original was a function, but the inverse is not. And that may be the case every once in a while. Let's look at the second example. I'll go back to my blue color. And we have, again, some key points here. A point of 6, 0, 0, 4, and negative 6, 0. And it doesn't matter what points you use. I always just tend to use x and y intercepts and then draw the shape through those x and y intercepts. So I'm going to use 0, 6 as one of my starting points, and I'm going to go to 4, 0. That's half my curve. So I'm going to go 0, 6 to 4, 0. So there's part of my curve. And the other one I'm going to go to is negative 6, 0. So we'll switch x and y, and then redraw your graph. So again, this graph, switch your coordinates and redraw the shape through those switched coordinates. So 6, 0 became 0, 6, 0, 4 became 4, 0, negative 6, 0 became 0, negative 6. Now that I look at that, that's backwards. And fix that point. Now, is this a function? No, again, this wouldn't pass the vertical line test, so this is a case where it's not a function as well. These can get a little bit complicated the first couple of times you start to switch, but if you want to take your coordinates and write them off to the side, and then just write them in a particular order from left to right, then graph from left to right, that may help you plot your points. I know a lot of times when students start switching, they don't know from which point to go to which point. You have to set this up so this works for you. Some people can just replot all points and then draw a shape through it. Some people have to go point by point and then connect the dots as they go through. However this works for you, all we're doing is we're switching coordinates, redrawing, and then determining whether we're a function or not in these two examples. Again, this is a reflection over the line y equals x. It's a little hard to picture, But if I draw it in for you again, something that you'll have to get used to trying to picture as time goes on. The line y equals x looks like this. And you can see that they are mirror images over that line, meaning that the distance that the red graph is away from the line is the same as the distance that the black graph is away from the line. They are mirror images on that line. So you can reflect on the line y equals x if you're one of those people that can do these visually. If you're not, and I'm not one of them, I always have to take coordinates, switch them, redraw it, and then look at the line y equals x after for that picture. Alright, so there's two examples of you actually having a graph, which is just a series of points. Take some key points, enough to actually identify the original shape. X and y intercepts are usually good enough. Switch those and regraph. Let's look at a third example where we have an equation. When you have an equation, first thing you do with an equation is you just switch x and y. So the first thing I would do is g of x stands for y. That now becomes x, and where you had x now becomes y. So the very first thing I do is I switch x and y and write the inverse, and then the next thing I do is I solve for y. So add 4, x plus 4 equals 5 halves y. Multiply both sides by 2/5 to get rid of the fraction. Remember, it's 2/5 times the whole thing, so it becomes 2/5 times x plus 4 equals y. And since this is a linear function, right, it's a degree 1, we know that this thing would be a function without even graphing. You could graph it on your calculator to check, but if it's a function, you're allowed to use the notation that identifies it as a function. So I can write this as 2/5 x plus 4. And that's what my inverse is. And what does that mean? If I was to graph the original g of x, 5 halves x minus 4, and graph the inverse, they would be reflections over the line y equals x. That's all it is it's just another graph that has a very special relationship to your first graph. And they are reflections on the line y equals x. It's a special graph. Just like if you flip it over the x-axis, it's a special type of graph. Flip it over the y-axis, it's a special type of graph. Flip it over the line y equals x, it's another special type of graph. In Pure Math 30, you're going to work with many different types of reflections. This is one of them, and it's one of the more complicated ones, which is why I'm giving you kind of a little bit of a heads up in this course, so that when you see it in Pure 30, you'll at least recognize a few little things from this course. So if you have an equation, switch x and y, solve for y. Last one, let's just do a comparison of a function that we've already looked at. In the last lesson, we've looked at rational functions, so we've talked in detail about asymptotes, domain and range, and all of that. Well, let's apply the concept of inverse. Again, the first thing you always do is you take your denominator and you find your restriction. X minus 4 cannot be equal to 0. X cannot be equal to 4. That tells you what your asymptote is. Your first asymptote will be x equals 4. That also tells you what your domain is. X such that x cannot be equal to 4. And you'll end up graphing this to check this out, but we know that right from the last lesson when we studied rationals, that if you find the restrictions will tell you where those asymptotes are, and it'll tell you your domain and range. Now again, if you compare the degrees, the degree of the denominator is greater than the degree of the numerator. So from the last lesson, this should tell us that y the horizontal asymptote will be y equals 0. Again, if you don't memorize that little rule, then what you're doing is you're graphing and you're looking to see what value the graph approaches on the extreme left and extreme right. But if you've got that tips memorized, you would know that as soon as the degree of the denominator is greater than the degree of the numerator, you know that your horizontal asymptote will be 0, which then tells you that your range cannot be 0. So as soon as you know a little bit about the function, you can get asymptotes and domain and range. That's from the last lesson. That's nothing new. Inverse is going to tell us to switch x and y. So if we want to find the inverse from the equation, we will write this as x equals 2 over y minus 4. And we have to solve for y. So the first thing we'll do is we'll multiply both sides by y minus 4, and it gives us x times y minus 4 equals 2. Get rid of the x, so I'll do this on the left side. So it'll be y minus 4 equals 2 over x, and our final answer will be y equals 2 over x plus 4. There's my inverse, and if it's a function, which this is, I can then write this in function notation as the inverse. And again, this notation is just telling you that this is a function with a special relationship to your original. 2 over x plus 4. That's it. People get a little bit bent out of shape of what that symbol recognizes, and all it's telling you is when you see f to the negative 1, it's telling you that there's a special relationship between this graph and its original. And that special relationship is that it's a reflection on the line y equals x. I've been highlighting that pretty much the whole lesson. So this is something that as soon as you see that notation, you don't have to go through and say, oh, it's just a different graph. It is a different graph, but it's got a very special relationship to the original. It's the only graph that would be a reflection on the line y equals x. So that's why we can give it a very special notation because of it. Now, if you wanted to enter this on your calculator, in fact, I recommend you do. But if you really understand the concept of inverse, and meaning that it's a switch of x, switch of y, switch of domain, switch of range, if you want to answer the last two questions, the asymptotes of the inverse will mean just the switching of the x and y values. So if the original had x equals 4, y equals 0, the inverse should have x equals 0, y equals 4. And if you actually graph that inverse, which I'm on a different computer this time, so I don't have that graphing calculator that I used in the last lesson, you would see that. If you graph 2 over x plus 4, you would find that your vertical asymptote would now become x equals 0. Your horizontal asymptote would become y equals 4. Why? Inverse means to switch x and y. So you switch the equations of the asymptote. What does it mean for the domain? Well, you switch the domain. What was originally the domain is now the range. What is originally the range is now the domain. So on the inverse, we will now write the domain as x such that x cannot be equal to 0. And the range y such that y cannot be equal to 4. So the real neat thing is, when you're dealing with a function and its inverse, once you know domain, range, and asymptotes of one, you also know the domain, range, and asymptotes of the other, because it's just a matter of switching x and y, which means you switch the equations of the asymptotes, you switch the domain and range. And if you graph this, you would see that. on your other graph. Alright, that's our last lesson. What I want you to work on is exercise 5.6. Really practice finding the inverse algebraically by switching x and y, solving for y, and practice graphing these so that you can see the original, see the inverse, and it helps you picture that reflection on the line y equals x. The more you see it, the more or the easier it will become, because it is a very difficult concept the first time you look at it. Keep remembering what inverse is. It's just a special graph that reflects your original on the line y equals x. And how you find it is you switch x and y, solve for y, or switch your coordinates. So do exercise 5.6. Take care, everyone.